Our next speaker is Kristina Flavier. She is a senior scientist in the physical sciences group from FreeThink Technologies Incorporated in Brantford, Connecticut. Her focus is on understanding the factors that influence physical and chemical stability and supports clients in solving complex stability problems. She uses the Accelerated Stability Assessment Program, ASAP, nicely named, approach and FreeThink's ASAPprime software to predict shelf life and recommend optimal packaging conditions for products in the pharmaceutical, food, and consumer healthcare industries. So I'd like to hand you over to Kristina, who was now going to give us her talk entitled Predicting Shelf Life with the Accelerated Stability Assessment Program, ASAP and ASAPprime. Thank you, Kristina.
Yeah, thank you. Okay, so today I'll be discussing the ASAP approach and ASAPprime software, which is what we used for the modeling. So to quick outline of what I'll be talking about today. The first part of my talk will concern ASAP to predict stability. So in particular, I'll be going over the kinetics of degradation, the isoconversion approach, which is what we actually use to determine what the shelf life will be, the humidity modified Arrhenius equation, and the statistics, which make up a big part of the ASAP predictions. After that, I'll be going through two case studies. The first one will be looking at degradant growth, with a focus on the effect of packaging. And the second case study will be looking at color change. So the first question is, what is ASAP? So ASAP is a method of predicting stability, predicting long-term stability in a much shorter time frame. So the way we go about this is first, the product, API drug product, is exposed to high stress conditions outside of packaging, so under open conditions. Because the goal is to finish the study quickly, we go to a higher temperature range. Usually this is 40 to 80 or 90 degrees Celsius. And the relative humidity range spans the entire range from about 0 to 80% RH. By going up to these high temperatures, this allows us to stress the tablets and see degradation in a much shorter time frame. So usually about 3 to 4 weeks stress is what we use. At the end of that stressing period, we measure the shelf life limiting characteristic, whatever that might be. So anything that follows the Arrhenius equation can be used with ASAP. Most often that's related growth of related substances or loss of assay, though we have also done color and dissolution studies. Viscosity and probiotics also follow the Arrhenius equation. So once all of this data is in hand, you can put it into the ASAPprime software and apply the effects of packaging to determine what the shelf life is going to be.
Kristina, sorry to interrupt you. We've had a request. Could you just speak a little bit louder, please?
Yeah, I tried moving the microphone a little bit closer. Is this okay?
That's a little bit better. Can you do that same thing again, or?
This is about as close as I think as I can get it.
Okay, it does. It did help. It did help what you did. Thank you.
Mm-hmm. Okay. So the advantages of the ASAP approach, because we're stressing at a number of temperature and relative humidity conditions, this allows us to deconvolute these two factors. So we get a fundamental understanding of the temperature and humidity dependence for your particular product. This means that if you're considering a change in packaging, most often that's going to be related to the relative humidity that your product experiences. Since we know the relative humidity dependence of degradation, then you can say, okay, this is how it's going to affect the shelf life. Similar for excursions, because we know what the temperature dependence is or the RH dependence, you can say, okay, if it sees a higher temperature for 1 week or 2 weeks, how is that going to affect degradant growth? It also aids solutions for stability problems. It can say, would you be able to make your target shelf life with a packaging change, or are you going to need to go to a lower temperature? The other big advantage is the speed. So if the traditional ICH approach requires testing for at least 6 months, up to 2 or 3 years to set shelf life, an ASAP study, as I said, it's usually a 3 to 4 week stressing and then analysis and modeling. So in about 5 to 6 weeks, you can know if this formulation in this packaging at this storage condition is predicted to make your 2 or 3 year shelf life. So talking about the kinetics of degradation. So accelerated aging approaches that have been used in the past are often not predictive of real-time stability. Um, in part, this is because a lot of products show complex kinetics that can't be fit to a linear approach. There's a few different reasons for that. I'll go through a few examples here. One of them is heterogeneous kinetics. So, for example, if you had a tablet consisting of API, say crystals of API and excipients, if you had a molecule of API that's in the center of this crystal, the assumption is it's going to be pretty stable. It's going to see a little bit of slower degradation. So that's what this red line here is. This might be the rate of degradation for API inside that crystal. On the other hand, if there's a molecule at the outside of this crystal that's in contact with the excipient, in general, that is going to exhibit faster degradation. So that's the green line here. But the other thing to consider is that there's only so much API that's in contact with excipients. As that gets exhausted, then the rate of degradation begins to slow down. But of course, we don't measure the degradation of individual API molecules. So what we actually see when we do an analysis on a drug product is a combination of these two degradation rates. So it can be like this blue line here. So you see it's neither simple, it's neither simple kinetics and it's not linear either. Another example is the case of secondary degradation. So here, if you have a drug that degrades to a primary degradant, this light blue line here, that degrades further to a secondary degradant, the dark blue line. As the primary degradant starts degrading, the amount that you measure, the rate at which it grows, seems to slow down because it's being consumed. In contrast, the secondary degradant requires the primary degradant to form. So there's a little bit of time at the beginning here where it doesn't immediately start to grow. The result of this is that, well, both of these are nonlinear, and depending on your specification limit, your shelf life limiting degradant might be different. So in this case, if you have a 0.2% specification limit, you see the primary degradant is reaching it first. With a higher specification limit, 0.5%, it's actually the secondary degradant that's shelf life limiting. So going back to the kinetic models, um, prior approaches to accelerated aging haven't always been predictive of real-time stability because of varying kinetic order and because of complex kinetics. I talked about heterogeneous systems and secondary degradation. A couple other examples are autocatalysis, when degradation leads to faster degradation, and inhibitors. A common example of this would be antioxidants. Um, if your API is prone to oxidative degradation, then it's not going to see much oxidation until the antioxidants are completely exhausted. So you would have a lag phase before you see the oxidative degradants start to grow in. So the question becomes, can you perform kinetic model in the absence of detailed kinetic studies? And so the approach that we use for ASAP is called isoconversion. So this graph is just an example of how accelerated stability studies have been conducted in the past. We can focus over here, where there's just a single time point, in this case at 21 days, and multiple different temperatures. So we measure at this 21-day time point and say, okay, at 70 degrees Celsius, we see about 0.8% degradation. Because we only have this single point, the best estimate of the rate of degradation we can get is the slope of this line, the 0.8% degradation over 21 days. So about 0.04% degradant per day. And then this is done for the 70 degrees, 60 degrees, 30 degree temperature. The problem here is that with a single time point, we're assuming linear behavior. You can see in practice that these dark lines here, the solid lines, show what the degradation behavior might actually be. It might be a curve, it might not be linear at all. So here we're actually hitting the specification limit much longer than we're calculating from this constant time point measurement. So what happens when we fit those rate constants to the Arrhenius equation? It appears very non-Arrhenius. We don't have a nice linear fit between 1 over temperature. This means that we can't use the high temperature results to predict shelf life at the relevant storage conditions. So what the isoconversion approach is, isoconversion is the time to the edge of failure. So this is measuring as accurately as possible the time to reach the specification limit, whatever the specification limit might be. So growth of a specific degradant, total degradant, loss of potency, so on. So here you can see we're looking at the same kinetic forms. Again, we have these curved shapes at 70 degrees, 60 degrees, 30. But here we're measuring at multiple different time points and trying to find as accurately as possible when we reach this specification limit. So in this case, the rate that we're calculating is the specification limit, 0.5%, divided by the time to reach the specification limit. So 0.17% per day is what it comes out to here. You'll notice in this case, because we're measuring the time to reach the specification limit, it doesn't matter what the kinetics are to reach this point. Whether we have a curve shape, or whether we have a line, as long as the time to reach the specification limit is the same, then the calculated K does not change. So when we use the K values calculated in that way, we do get a good fit to the Arrhenius equation. And that allows us to predict the shelf life at lower temperature conditions, irrespective of the kinetic form. Going back to the Arrhenius equation. So this is the traditional form. ln K, where K is the rate constant, the specification limit over the isoconversion time, equals ln A. This is the intercept. This is going to vary depending on formulation, on your API, a bunch of different factors, minus EA over RT. So the EA over RT here is the temperature, it's the temperature term. EA is the activation energy. Based on, and this based on the EA, then you might have a lower high temperature dependence of degradation, basically saying as your temperature changes, what is the impact of that going to be on your degradation behavior? In ASAP, we actually incorporate one additional term, which is the humidity sensitivity factor. So this is B times the relative humidity. Similar to the temperature sensitivity term, this just says as your relative humidity changes, what is the impact going to be on your stability? Looking at the EA and B values here. So say that you did a real-time stability study. You know that you are stable, that you reach the specification limit in 6 months at 40 degrees Celsius. So the ICH assumption is that 6 months at 40 degrees Celsius is about equivalent to 2 years at 25 degrees Celsius. That assumes a particular activation energy, a particular temperature dependence. In actuality, that's about 17 kcals per mole. That is lower than what we've historically seen. On average, what we see is an activation energy of 29 kcals per mole. So what you see as we go up in activation energy, it's a stronger dependence on temperature for degradation. So you get a longer shelf life by going down in temperature. We can go even higher in activation energy. So, sometimes we see products with with an activation energy of 40 or 50 kcals per mole. And that would say if you had 6 months if you were stable for 6 months at 40 degrees Celsius, maybe you'd have a 12-year shelf life at 25 degrees Celsius. In the absence of any other information, you couldn't say which of these regimes your product falls into. So the ASAP approach, because it stresses at multiple different temperatures, it allows you to determine for your drug product what your activation energy is going to be and where your shelf life, how long your shelf life is going to be. Another thing to note is that though 17 kcals per mole is a much lower activation energy than average, it's not entirely unusual that we see products with even lower activation energies, sometimes down at the 12 or 15 kcal per mole, in which case 6 months at 40 degrees Celsius might lead to an even shorter shelf life at 25, which is another reason why it's useful to know actually what your particular activation energy is. Similar to that is the B factor, the humidity term. In this case, say you have 5 years, you're stable for 5 years at 60% RH in a PVC blister. So PVC is a pretty permeable packaging. The assumption here is that you equilibrate pretty quickly to the exterior 60% RH. So if you went up in humidity, if you went to 65% RH, and you had a B term of 0, this is actually no moisture sensitivity. That says that no matter what your relative humidity is, your shelf life is not going to change. It's 5 years either way. In practice, the average that we see is usually about 0.037. This 5% increase in RH therefore leads you to a 3.8-year shelf life. On the other hand, an even higher moisture sensitivity cuts your shelf life even further. And one thing to note here, actually, is that this 5% difference is within the tolerance that's allowed for humidity chambers. So depending on your packaging and the moisture sensitivity of your product, you might actually see a pretty big difference in shelf life just from that 5%. The higher the B factor, the higher your moisture sensitivity, the more your product stability can be controlled with packaging. If you're not stable in the PVC blister, then switching to something slightly more protective, like a PVDC or Aclar, would have a greater effect. In contrast, again, if you're not moisture sensitive, it doesn't matter what packaging you put your product in, the shelf life is not going to change. This scatter plot just shows some of the typical EA and B values that we've seen from drug products and APIs at FreeThink. Again, the average is about 27 kcals per mole for the EA, though sometimes we see down to 10 kcals per mole or up to 50 or higher. The average B value is about 0.37, but some products have almost no moisture sensitivity. Some have a very strong moisture dependence. The next thing I'd like to talk about here is the statistics of the predictions. So remember that for the ASAP approach, we're trying to reach the specification limit in 3 to 4 weeks, which requires stressing at pretty extreme conditions. So some of the examples here is 80 degrees Celsius, 40% RH, 70 degrees Celsius, 75% RH. Each of these conditions is going to have an error bar in the prediction. So some of this is just due to the analytical method, variability in the analytical method. Some of it is due to estimating the ISO conversion time. So, maybe you think you reach the specification limit about 2 days, but that might be 2 days plus or minus 0.2 days. When you're extrapolating from these high temperature conditions down to relevant storage conditions, in this case 2560, then the error bars are going to grow much bigger. So at these high temperature conditions, we can accurately determine the ISO conversion time at each condition, but it still is going to give a big error bar at 2560. So the way this is handled for ASAP is actually with a probability distribution. So in this case, this probability of passing is specified times. For this particular distribution, the mean comes out to about 94.7 days. That case, we would say the average shelf life is about 95 days. The problem with an average, of course, means that you have a 50% probability of passing, which is a 50% probability of failing, which is not something you want to go forward with. So usually what we like to say is if you have a 95% probability of passing or higher, you can say that you're sure that you are stable at that particular condition for that particular length of time. So here, using the ERF function to determine probabilities, these are the standard deviations. The 98% probability shelf life is about, I think, that's about 32 days. So you would say, okay, there's a 98% probability. We're pretty sure we're stable for those 30 days. I won't go into too much detail about how the study design today. If you have any questions about it, you can ask later, but this is just an example of what it might end up looking like. So the study design takes into account a few different factors. You can tell it what kind of product you're looking at. If you're looking at a liquid, if a tablet, a LIO, it has parameters for each of those. Your target storage conditions. If you have any prior stability data, it knows how harshly you need to stress your product to reach the specification limit, and if there are any phase transitions that it should avoid crossing over in the course of the study. So with all of that information others taken into account, it generates something like this. So this dark gray area in the middle is the space where it thinks you will reach the specification limit in the time allotted for the study. So you can see here we said, okay, 21 days is the maximum time we'll allow for the study. Based on that, it gives a temperature range from about 50 to 80 degrees Celsius and RH conditions from about 20 to 80%. So with that in hand, this is the experimental setup we use at FreeThink. So we use actually ball mason jars as little chambers for each of the samples. These have been shown to hold seals up to 90 or 95 degrees, which is the highest we go for ASAP studies. Inside these jars, we'll have the sample. In this case, it's just a capsule in a little dram vial, a saturated salt solution in a vial with a permeable cover. So this is usually what we use to control RH. There's extensive literature on the equilibrium relative humidity above saturated salt solutions, different saturated salt solutions. This is a good reference that contains many of them. The ASAPprime study designer, if you choose to use saturated salts, it has a number of saturated salts included, and it will say, okay, to reach this particular RH at this temperature, this is the saturated salt you'll want to use. And the last thing in this example is just a temperature relative humidity data logger to be sure that you reached the target values. Okay, from there I'd like to go on to the two case studies that I have today. The first case study concerns growth of a degradant in tablets. So this is data for a model tablet drug product that was produced at FreeThink. Um, so on the top panel here, this is the actual experimental data on degradation that we collected. The 0-day time points are 3 replicates of control unstressed tablets. And then from there, you can see some of the stress conditions, like 50 degrees C, 30% RH, 4, 9, 21 days. The first thing we're considering here is what is the shelf life going to look like in the absence of packaging? So if we look at the degradant plot, it's currently set to 25 degrees Celsius, 60% RH, so predicting shelf life at those conditions. And it says for a 2-year, if our target shelf life is 2 years, the pink line here, we are basically not going to make the shelf life. There's a 0.6% probability of passing. The blue line here is the mean shelf life. That's at about 1.1 years. The green and red lines are 1 standard deviation. So what this is saying is this particular product outside of packaging is not going to make it. One thing you might note is that the specification limit for this is 3%. This is a pretty well-known API, and this is a known degradant, so we can use a high specification limit for this. But in practice, it can also, of course, be used for much slower specification limits. We're often looking at the 0.5% or 0.2% spec limits for degradants. So this is an example of the experimental data for degradation. So you can see each of these plots is a 1 temperature relative humidity condition. The top left here is 50 degrees C, 31% RH, 50 degrees C, 51% RH, so on. You can see here we're actually getting the green line, the fit to the data. It's linear. So this is a case where we do have linear kinetics. Um, if you remember the goal for an ASAP study design, we would like to measure the time to the specification limit as closely as possible. So there's a few conditions where we have points that are very close to that. So this 50 degrees C, 51% RH, the top center here, we have a 9-day time point, the blue line, the blue dot, and the pink line here is predicting a 9.04 isoconversion time. The one next to it, 6021, again, it's the same. We have a 4-day time point, and it's predicting a 4.3-day isoconversion time. In cases where we are not quite at the specification limit, in all of these graphs, we're actually bracketing it. We have a time point before or above and below the specification limit. So that allows us to interpolate rather than extrapolate the isoconversion time, which gives us smaller error bars. And so if you look at the data, you can see that there's both the temperature and humidity dependence for this degradation. So the top left 5031, we're looking at a 13.7-day time to reach the specification limit. If we go up 20% relative humidity, we are reaching specification limit at 9 days. So as temperature increases, as humidity increases, we are seeing degradation speed up. So then going back to the software, what it does is at each of these stress conditions, we're finding the time to reach isoconversion at each stress condition. That's just what this table here is showing. The third tab up here gives the parameters for the Arrhenius fit. The LNA, again, is the intercept. The EA is the temperature sensitivity. Now remember that the average EA is about 28 kcals per mole, and this is 32. So we're just a little bit above the average temperature sensitivity. The B term is right about average. So the average B term is 0.037. We're at 0.034. This means we can affect our shelf life by putting it in packaging. The last two numbers here, the R squared and Q squared, they're just both measurements of how well the data fit the model. Both of these are a q squared above zero 0.7 is generally considered good. These are both above 0.95. So these are, it's saying this is a pretty good model. There's a few other ways in the software to measure this as well. But okay, so the next thing, since it's pretty clear these tablets are not going to make the desired shelf life outside of packaging, next thing to consider is what is the impact of packaging? So for a lot of products, what packaging is going to do is it's going to affect the relative humidity that your product sees over time. In our experience, solid products are usually packaged at about 35% RH. Remember that typical storage conditions might be 2560, 4075. So you'd have a much higher RH outside of the packaging than inside. What this means is that the relative humidity inside the packaging is going to change over time. And this is controlled by the rate at which water permeates inside the packaging, which is the moisture vapor transmission rate, the MVTR. So water comes inside the package based on the MVTR, and then it equilibrates with whatever is contained inside your packaging. So the tablets, if you have, will pick up water. The desiccant will pick up water. In practice, actually, most of the water that goes into packaging is going to end up in tablets or desiccant rather than staying in the headspace. The amount that goes into the tablets is determined. It's by what's called the moisture sorption isotherm. So this just relates the water content of your product or of a solid to the relative humidity. It might say, okay, at 35% RH, your tablets will contain 1% water. So looking at that in the context of the program, um, so if we look at the bottom half of this panel here, so the software contains the ability to basically build your product. It contains information on the moisture sorption isotherms of a bunch of different excipients. So that's what was used here. So you can see it selected API. This is a generic crystalline API, assumed not to take up very much water, microcrystalline cellulose, mannitol, etc. Um, what the software then does is, because it has the moisture sorption isotherm of each of these, it takes the weighted average of those to generate the moisture sorption isotherm for the whole product. And so you can see what this plot on the bottom is showing. At 50% RH, then a tablet with this particular formulation is going to contain about 1.8% water. And there are also other options to custom load moisture sorption isotherms. If you have data on your own product or on your own API, that can be included as well. So then what the software does, if we look at the top half here, there's an option for packaging selection. So the options are bottle, blister, bulk, and it contains MVTR data for a number of different materials. So it might have PET bottles, HDPE, glass, blisters, PVC, PVDC. You see the current selection here is 2 mil Aclar. What this packaging option really does here is it says, okay, what's the MVTR of your packaging going to be? The custom option says if you know what your MVTR is for your own particular packaging, you can use that as well. So what the software does is say, okay, we know what the initial RH is inside the packaging, we know what the storage RH is, and we know what the MVTR is. So we know how quickly water will permeate into the packaging. And then we have the moisture sorption isotherm that says, as the RH changes, how much of that water is going to go into your tablets and how much is going to stay in the headspace. And so these two factors are combined to generate this plot here that shows the relative humidity inside packaging over time. So to predict the shelf life for your product, there's two things that are taken into account. One is building the stability model. So by stressing at a number of different temperature and relative humidity conditions, you can determine the temperature and relative humidity dependence. This also means that because it's an equation, because you know explicitly um, what these two things are, you can model at any temperature or relative humidity you feel like. So you can do 2560, 4075. Sometimes for the food industries, they want stranger conditions. So maybe you want to know what it is at 23 degrees or 20 degrees. or 8 degrees rather than 5 degrees. Because you have because you know explicitly what the activation energy and the moisture sensitivity are, you can build the stability model considering any of those. The next part to take into account is the relative humidity inside packaging as a function of time. So this is assuming it's all at a set temperature. Um, as water permeates into your packaging, as the relative humidity inside the packaging changes, the software says, okay, this is how your degradation rate is going to change. And by combining these two factors, then the stability inside packaging can be predicted. So going back to our tablet example here, again, this is an example of what the shelf life looks like in the absence of packaging. Um, no chance of passing 2 years. The average shelf life is about 1.1 years. So now what happens if we put it in bottles? So you see now these are in 60 cc bottles containing 10 tablets. The formulation here, it's 200 mg tablets, so 10 200 mg tablets. It's a little bit better. Our average shelf life is now up to 1.2 years, but you can see we're still at a 2% probability of passing. Still not going to make that 2-year shelf life. So then what happens if we add desiccant? So over here now we have 1 gram of silica gel desiccant that's incorporated into the packaging, and that makes a huge difference. Now we're at 100% probability of making the 2-year shelf life, and the mean shelf life is over 3 years. So we took those tablets and then put them up at 2560, 3065, and 4075 for 1 year. So here you can see the blue line here is the mean predicted shelf life. The green and red are the error bars. And the black dots are the actual measured percent degradant. So we have a really good match to the model in these cases. Top line here, bottles, no desiccant. Um, you can see actually up to the 4075 at the 6-month time point here, we're up at 40% degradation. um, ASAP, so this approach, if you remember, we're focused on on isoconversion, the time to reach the specification limit. So we're really looking at the behavior up to the specification limit. Anything past that, if you failed, you failed. It's not really of interest. Even so, we're still within error at the 40% degradation level. Now, when we look at bottles that contain 1 gram of silica gel desiccant, again, we have a really good fit to the model predictions. And we were predicting that we would have the 2-year shelf life at 2560. Okay. So the second case study I'd like to go to here is a little bit more of an unusual case.
Sorry to interrupt you. It's just we're already 5 minutes over. Can you wrap this up in a couple of minutes, or is that a good place to stop?
Wait, did we start at 2:30?
Yes, actually, Pauline,
I'm so sorry. I'm looking at. I didn't print out this. I'm so sorry.
No,
Carry on.
I'm a little confused.
I was looking forward to the second case study. Okay.
Okay. Yeah. Okay. So this is a little bit more of an unusual case. So it's a color ASAP study. So other shelf life limiting factors can be modeled using ASAP and the isoconversion approach. If you remember, if it follows Arrhenius kinetics, then we can model it. Color change is the result of a chemical process and therefore has Arrhenius behavior. So color is an interesting case in that historically it's been judged quantitatively. So you might see an appearance might be, it needs to be white to off-white. But at what point does it stop being off-white and start being an unacceptable color change? The other thing about color is that while it doesn't necessarily affect how well your product performs, it's often more of a patient compliance question. So color change is not necessarily due to degradation of the API. It might just be something in the coding. But for example, if a patient opens a bottle and sees, okay, these tablets have spots on them, I don't want to take these tablets, then yes, that is a factor that is going to limit your stability. So how do we treat color ASAP studies? The first thing to model color, we need to be able to quantify color. We need to be able to set a specification limit so we know when this has failed. The way we do this at FreeThink, we use the CIE L star, A star, B star standard. In this case, L star, it well, the L star, A star, B star standard measures color against three axes. L star is dark versus light on a scale of 0 to 100. A star is green versus red, negative and positive axes, and B star is blue versus yellow. In practice, any of the metrics that quantitate color can work with this approach. It looks like it's not displaying properly, but usually what we see is that when color change occurs, there are changes in two or more of these axes. So we actually calculate total color change using the CIE 76 formula. So this is called delta E star, and it's just a metric that measures the change in each of these axes versus a control sample. So what does this actually look like? So for this study, we formulated indigo carmine tablets that contain lactose. So there is a known incompatibility between indigo carmine and lactose. The lactose causes a reduction in the dye that leads to a fading or yellowing of the color. So that's what you can see on the image on the left over here. The bottom sample here is a control sample. It's a nice dark blue. But upon stressing at 80 degrees C, 73% RH for one day, we have a whole lot of fading. Um, so when we look at the L star, A star, B star measurements, control compared to the stress samples, the stressed samples are showing a higher L star, so that's a movement toward the light, toward the whiter. A star is about the same. B star, there's an increase moving toward the positive. So that's a movement from the blue towards the yellow axis. When we calculate the delta E star of these tablets is about 9.3. So for the purposes of the study, we said, okay, we can set a delta E star of 10 as unacceptable color change. Of note, because this is a specification limit we're determining as part of the study, you can set the delta E star to whatever seems appropriate. So if we said this is too much color change, we could use a delta E star of 4, 5, or 6. Delta E star of 2.4 is considered usually just visible color change, but that'll depend on the color you're looking at. So in this particular example, yes, one other thing to note is because the color measurements are actually across the sample, it averages the color seen in an area. So if you're getting sample spotting, uneven color change, that can also be accounted for just because it's taking the average. So what does this look like? Okay, so again, stressing at high temperature and a variety of relative humidity conditions. This is an example of one particular temperature and RH condition. You might remember in the previous example for degradant growth in tablets that actually had linear kinetics. In this particular case, we see what we call the diffusion fit, where we have faster change at the beginning that slows down over time. And similar to the degradant example, we're plotting the y-axis here is just the change in the stability indicating parameter. In this case, the delta E star versus time. Experimental data for color change. Again, at several of these conditions, we're bracketing or at the specification limit. This is a 30-day study. In some conditions, like the one I just showed you, we're extrapolating to reach the specification limit. So that leads to a little bit of a bigger error bar. So putting this all together into the Arrhenius equation, we get that the activation energy, the temperature dependence, is lower than average. It's about 23 kcals per mole versus the average of 27. The B value, the humidity dependence, is much higher than average. So remember the average there is about 0.03. We're looking at 0.08. So what this is saying is, putting this in packaging, we should see a difference in the shelf life. And again, the R squared, Q squared, the statistics say that this is a good fit to the model. These four plots show the predictions for shelf life at 2560 and 4075 without packaging and in HDPE bottles containing 5 tablets. So you see at 2560, it's an okay probability of passing, about 86% chance of making 2 years. 4075, there's basically no chance, a 0.17% probability of passing. If we put these in packaging, just 5 tablets in a bottle, then we make the 95% probability we want at 2560. Even then, at 4075, we're not going to pass. And so this is actually one of those examples where, the ICH guidelines don't quite capture the situation. So the assumption that 6 months at 4075 is equivalent to 2 years at 2560 does not hold in this case. So the real-time data over 9 months for 5 tablets in a 60 cc HDPE bottle. So you can see again, we have a pretty good match between the experimental data and the model predictions at 2560, 3065, and 4075. And you remember the model predictions said that the tablets would be failing on color when they reached after 6 months at 4075, and that's the case here. So you see the delta E starred here is about 11, passing our specification limit of 10. So to conclude, accelerated stability can be applied effectively to set shelf life with ASAPprime using the isoconversion approach, so focusing on the time to reach the specification limit, accounting for both moisture sensitivity and temperature sensitivity, and using statistics to account for the extrapolation down to lower temperature conditions. ASAP can be used to accurately predict shelf life limiting parameters in packaging. In this case, I showed examples of degradant growth and color change. And ASAPprime enables better decisions to be made in a much shorter time frame. Okay, so I'd like to acknowledge the teams who worked on both of these case studies for the related substances and color case studies. Ken and my colleagues at FreeThink, IPA for hosting this conference, and then all of you for listening. Thank you.